now. Now minimize. All right. There we go. All right. All right. Let me just take it back to the point where we kind of ended last time, where we talked about K sub C, which is the equilibrium constant based on concentration. That's what the little c is for, right? And what it is really just a ratio of rate laws for this reversible reaction. So we have a reaction going forward, a reaction going in reverse. When they reach equilibrium, we could write the rate laws for each one of these reactions and set them equal to each other. And that's really a unitless ratio of concentration of products to concentration of reactants, right? So it would be, to put it generically, it would be concentration of products over concentration of reactants raised to their coefficients. Okay. So let's kind of step through it a little more. We talked about what it would look like if you just have something that has more than one or two reactants and products. Step through that. We talked about what has a concentration. So what has a concentration? Aqueous solutions and gases, right? Everything else, solids, right? Once you have a solid, it doesn't have a concentration. You can't make it more solid, right? Or less solid. Same thing with liquids, with pure liquids. So we're not talking about, say, for example, if I have a sodium chloride solution, I can make that more concentrated or less concentrated. What I can't do is if I take, so say, for example, sodium and I melt it and turn it into a liquid, there is such a thing as liquid sodium, that doesn't have a concentration. That is just a straight up 100% sodium liquid. So we can't have a concentration for that. So we're really going to be working with gases and aqueous solutions. All right, so we did that. We talked about K sub P, which is basically the same idea, except with partial pressures of gases. This works when you have reactions that have gases in them. And again, it's that ratio of partial pressures of products to partial pressures of reactants raised to their coefficients. We'll see a little bit of that later, but we're going to stick with K sub C for the most part. All right. So this is kind of the new stuff here. What does it mean if we have a high value of K? So for example, if I had a K which with a really high value, I'm just going to make up a number, 54,000. I just made that up. What does that tell you about the concentration of the products versus the concentration of reactants? Algebra-wise. And we'll get away from the algebra in a second, but you have a higher concentration of products at equilibrium than a concentration of reactants, right? And that just gives you a really big number. So what does that really mean is in terms of a reaction, because you can't, AP doesn't like it when you say, well, the numerator's big or the denominator's big or the denominator's small. We're not talking about numerators and denominators. We're talking about concentrations of reactants and products. And what this means is, okay, if this is high, if the numerator is high, what we're really saying is we have a very high concentration of products. We're still at equilibrium, right? It's still dynamic. It's still going back and forth. These rates are equal, but when those rates become equal, we have a lot of product. We have a high concentration of product. We could say that it's product favored. And sometimes they say reaction goes almost to completion, which means it doesn't go to the end and stop, right? It keeps going back and forth, but it looks like you're pretty much there, right? You made a whole bunch of product. It is still going back and forth in this way, right? In this reversible reaction. So product favored means high concentration of products versus lower concentration of reactants. What if we had something, this is the opposite. If we had something, a K sub C, which is lower, right? Much lower. So for example, if I have a K sub C that is 0. And I'm kind of exaggerating here, but they get pretty small. That K sub C tells you what? That you've reached equilibrium and still going back and forth, but you have a very low concentration of products compared to the concentration of reactants, right? So if I was doing this in a flask, I would have and I was measuring what was inside, I would see a whole lot of my reactants that are still there, very little bit of my products that were made, right? They're there. I made them. It's a reversible reaction. There's some of this and some of that, but it's about concentrations relative to each other. And we would say that something like this, and this means that K is much, much less than 1, then we say it's reactant favored. Sometimes we say the reaction hardly proceeds. So it's happening back and forth, but it looks like you're really kind of stuck on the reactants. You're making very little concentration of products compared to the concentration of reactants. Just to put some numbers on it, this is really just kind of a rule of thumb. What is high, what is low? If you have a K that is less than 100 or somewhere between 100 and 1/100th, at that point, you're seeing reactants and products, right? So if I look in my flask and I have a K that's in here somewhere, I will see reactants, I will observe reactants, and I will observe products. They're in there, not necessarily in equal amounts, but in measurable amounts. Once we start getting much lower than this or much higher than this, it's definitely tilted either towards the product or the reactant. So again, this is not like a hard and fast thing, but if you see a question where they say you have a K of 99, 99, 99, or whatever that is, right? A big number, that means product favor. Yeah.
You want to indicate if it's product or reactant favored, would you draw like one of the arrows into equilibrium, like larger than the other one?
No. Good question. Yeah. So the question is, to the size of the arrows now, are we really saying that what do the arrows tell us? I'm glad you asked. The arrows are telling us the rates, right? So we're still going back and forth at the same rate. The question is, we're going back and forth at the same rate, but there's a whole lot more of this that's already there. And, we might be doing one molecule at a time or whatever, whatever we're measuring that rate at, but the arrows are the same. The rates are the same. We will get to a point where these arrows are not the same. That means that we're not at equilibrium. Yeah, good question. So yeah, let's make sure we keep track of those arrows. Those are rates. So yeah, don't try to show a situation like this where we have a really high or low K sub C with the arrows. Yeah. Good. Any questions on that? All right. So please don't say numerator and denominator is bigger or whatever. That's not the answer, right? We want a chemistry answer for this. All right. All right. Let's take a look at this problem. And see what we can do with this, right? So closed system. So again, we got a stopper on the flask, initially containing that concentration of hydrogen, this concentration of iodine. Here's our reaction. It's at 448. Remember, this is all temperature sensitive, temperature dependent. We reach equilibrium, reversible reaction. We look at the equilibrium mixture and we determine that this is the concentration of our product. And we want to calculate the K sub C. Is this just a question of plugging in numbers? You can tell by the way I asked the question, the answer is no, right? So what can we do? What's the first thing we can do that'll get us 1 point on the test that we don't really need any numbers for? What can we write? Yeah. What? Well, yeah, we don't necessarily want the moles. We can't really find the moles. Can we write K sub C? Can we write the K sub C expression at least? Yeah, let's do that because you get a point for that. And all we're saying is, look, I understand this is an equilibrium. I understand there's a relationship between the concentration of the reactants and products. So let's just write that first, right? At least get that point before we have to do something else. H2, I2. That's it. That's your equilibrium constant expression. We know that once we reach equilibrium, which is not these numbers, we're going to have this relationship between the concentration of the reactants and products. All right. But we still need concentrations. So go ahead and second, I just need to write some things down. I don't want to go back and forth on the screen since I'm recording. So, all right. So what can we use to get to some concentrations? What kind of cold table could we use? Yeah, let's use an ice table for this, right? So, or a rice table, because I like putting a reaction in there. So let's do that because we have some concentrations at the beginning and we have some concentrations at equilibrium. Remember that this E is not for end, it's for equilibrium. H2, I2, reversible reaction to HI. And this is where the ice tables kind of start to shine because they let us get to equilibrium concentrations, which lets us get to this, or vice versa, go backwards. All right, so we said the initial concentration of hydrogen, if I wasn't mistaken, it was this. Iodine was that. Remember, these are concentrations, not moles. And it didn't say that we had any at the beginning. So, and you will see somewhere the product actually starts out with a concentration, but not today, not now, rather. And then it says when we reached equilibrium, we had a concentration of product that was 1.87 times 10 to the minus 3. That's all we've got. What can we do from here? There's only one thing we can really figure out. Maddie, go ahead.
The change for HI is plus 1.87 times 10.
Yeah, right. We went from 0 to this. Well, there's only one thing that could have happened here is that we made this much of our product. That's the change. And then what can we do here? Well, we know that if we made this much product, the concentration changed this much, this had to change, right? And these are our reactants. These got used up in what ratio? 2 to 1, right? 2 to 1. So how much concentration did it drop here for each one of those reactants? Half of this, right? 1 to 2 ratio. So 9.35 times 10 to the minus 4. I know these numbers because I've already done them like 4 times. 9.35 times 10 to the minus 4. And then we can just do some math and figure out our equilibrium concentrations. So let's do some math and get our 1. 6.5 times 10 to the minus. All right. That seem right? Anybody else doing this? Yes. And then this would be somewhat different. Let me check my numbers, just make sure they're right. Yep, okay. So again, I mean, don't get too wrapped up in the numbers. What we're really saying is based on what this change is, we can figure out what our change, how much of this reactant concentration is used up. Now we have equilibrium concentrations for all of our reactants or products. What was the question? The original question. Yeah, calculate K sub C, right? Well, K sub C requires us to have equilibrium concentration. So at this point, and I'm just going to kind of fast forward the slides here, at this point, we just plug these in, and now it just becomes a plug it in exercise, right? Because once you have equilibrium concentrations, we can put them into our equilibrium expression that we already wrote 10 minutes ago and come up with a K sub C. K sub C is 51, unitless, no units. What does this tell us about reactant or product? Which one's favored? Yeah, this is product favored, but not a lot, right? If we looked in our beaker at this point, if we looked in our beaker, assuming it was still stopped up, we would probably have some measurable amounts, definitely measurable amounts of our product, but we would probably still be able to pick up some reactant there, right? Because it's not a huge K sub C. So it is product favored, but not a ton. So that's really what we have to be able to do. Any questions on that? Yeah. It means that, yeah, it means that the concentrations of the products and reactants are in an equal ratio. Yeah. Mhm. Yeah, I don't think you'll ever see one that's exactly one, but it's possible, I suppose. Yeah. Good. Any questions on that? All right, I'll tell you what we're going to do. We're going to stop here for the little work break. Those of you at home that are listening or watching the video, we're going to do problems number 11 and 14. So I'm going to pause the video real quick. And bing. Boop. Okay. All right, let's take a look at this problem. This one's slightly different, and we're going to have to do some different things. So we've got a reversible reaction. It's at equilibrium, and I've got my initial concentrations of my two reactants. Seems very similar to the last one. This should not say final. This should say, what is the equilibrium concentration? Final implies that it's done, right? And this reaction's never done. It's going to keep going, dynamic equilibrium, but they're giving you the case of C. All right, so this problem's a little bit different. We're looking for something different here. What's one thing we can do to start out without plugging any numbers in? Yeah, let's write the case of C expression, right? Let's write the equilibrium constant expression. And in this case, it's the concentration of HCl squared over the concentration of H2 times the concentration of Cl2. Remember, this is not plus, this is multiplying the concentrations. All right. And we know that's equal to 4.25. What are we looking for? We're looking for the concentration of HCl at equilibrium. So we know that we're going to put these two things together and we're going to make some of this, but then we're going to come back and go back and forth until we reach equilibrium. So how can we find equilibrium concentrations? Because we don't even know the equilibrium concentrations of this either. What can we do? What kind of cold table are we going to use? All right, yeah, let's use an ice table. That's always the answer, almost. Let's use an ice table for that. Now, this one's kind of pre-populated a little bit. So we're starting with our initial concentrations. Again, we're assuming we're not starting with any product. You'll see somewhere we do. But I don't have any of this, right? I don't have any of this, so I can't do what we did last time. But what do I know about the reactants? Reactants do what in a reaction? They get used up, right? These are gonna drop by a certain amount. This concentration is going to drop by a certain amount, and this product is going to go up, right? We're going to increase that. So I don't know by how much. So what do we do in algebra? If I don't know something, X. All right. So what I'm going to say is, all right, this is going to go down. Remember, these are molarities, right? This molarity is going to drop by a certain amount. What about this one? It's a 1-to-1 ratio. So it's also going to drop by X. What's going to happen to the product? 2-to-1 ratio, right? So this is going to go up by 2X. So I can find some equilibrium concentrations, right? They're not going to be pretty. They're not going to be numbers, but I have numbers, right? I have something. 2.0 minus X. This is 2.0 minus X. Right? We're getting rid of some. We're lowering this concentration. And then our concentration here is going to be 2X. All right, well, I love numbers, but this is what we got. However, we've got something we can put into our case of C. So again, concentration of HCl squared equals the concentration of our two reactants, 2.0 minus X times 2.0 minus X. So I'll drag this out a little bit. So what we're really saying is concentration of HCl squared over the concentration of 2.0 minus X squared. Oh, wait, that's not HCl. That's 2X. Not 2X squared, but 2X parentheses squared. All right. What do we know about this? If we got something squared on the top and something squared on the bottom, what can we do? Take the square root. And remember, this is equal. They gave us a value for this. This is equal to 4.25. So if we take the square root of both sides, and find a red marker. If we take the square root of both sides, we can actually solve this without using a quadratic equation. You can if you want to. I try to stay away from that, but we can solve this. and say, all right, well, now I know that 2x divided by 2.0 minus x equals the square root of 4.25, which is 2.06. I didn't do that in my head, I knew it from before. And now we'll just have an algebra 1 question, right? We can solve this for x. So go ahead and solve it for x. That algebra 1 or 2? That's algebra 1. 1.5. Solving for x. An x. James, you got an x for me?
1.015.
1.015, good. All right, so now in algebra, when you find x, yay, we found x. What was the question though? The original question. Yeah, what's the concentration of HCl? And the concentration of HCl was, or was it here, right? Well, that was 2x. All right, so our concentration of HCl, I'll put it up here, concentration of HCl was actually 2x, which means that's 2.03 units. Are there units on that? What is it? That's the concentration of HCl. Dang right, there's units. What is the units of concentration? Molarity, yeah. So don't just assume it's unitless, right? If it's a molarity, if it's a concentration, it's got a units of M, big F. Good. And what does that tell you? Well, that again tells you that if you put in these concentrations, when it reaches equilibrium, you're going to get to whatever that concentration is, right? So it's going to be about 1 molar, about 2.03 molar concentrations of each of those. Any questions on that? Okay, so we got to be able to do this. This is going to come in super handy when we start talking about solubility next week. We got to do this trick with the x's and the squares and stuff like that. All of the ones you see in AP are going to be squareable. So they call it the perfect squares. You'll be able to square this part, and you'll be able to square, take the square root of the case of C. All right, any questions? All right, that's the new stuff for today. Let me turn the recording off. And